It's my great pleasure to be here today with you. So from the earliest days, Honda Civics were known for their fuel efficiency. Quoting a Honda Civic advertisement, when we built our first Honda Civic back in 1972, we designed it as an answer to the world's transportation problems. Even that long ago, fuel economy was one of our prime considerations. Now, this is from an advertisement announcing the new Honda Civic that can deliver 42 miles per gallon. That's pretty good for a non-hybrid car these days, but this is an ad for the 1980 new Honda Civic. Now, fuel efficiency among automotives rose rapidly through the 1970s until the early 1980s, at which point it plateaued or declined for nearly 25 years. Now, granted, focus on fuel efficiency is subject to the whims of consumer interest, but the fact that it remains stubbornly stuck is less a function of a lack of engineering focus and more a function of the challenges and limitations of internal combustion engine technology. In fact, the primary reason that this chart reflects recent improvement is that automotive manufacturers began seeking technology solutions outside of internal combustion engine design. New types of drivetrains like hybrid gas-electric and all-electric and novel energy supplies, such as lithium-ion batteries and hydrogen fuel cells, have jump-started fuel efficiency gains, if you'll pardon the pun. Listening to the pundits lamenting the end of semiconductor innovation in the twilight of Moore's Law, it's hard not to feel like turn-of-the-century automotive engineers whose future was potentially limited by the laws of physics. So is the innovation party over for semiconductors? Is ours a future of fine-tuning and incrementalism? Well, as both an optimist and a student of the history of technical advancement, my answer is emphatically no. Now, before I delve into the rationale from my perspective, I'd like to set the stage by describing a few pervasive constants that are time-independent and will be the dynamics propelling us well into the future. First, innovation is as essential as energy and matter. As humans, we are programmed for exploration and adventure, and we possess an unquenchable thirst for knowledge and information. Second is the constant dance between the economy and technology. Novel technologies shape and reshape the economy, which begets further novel technologies, creating ever new challenges, and so on and so forth. Third, combinatorial innovation, the power of which is demonstrated by the evolution of automotive drivetrains to enable greater fuel efficiency. As Brian Arthur articulates in his book, The Nature of Technology, combinatorial evolution is foremost and routine. In many cases, unexpected applications emerge at the intersection with other technologies and physical domains. For example, the inventors of the digital camera certainly never had Instagram in mind, which was created by combining digital camera technology with software and the internet. Fourth, the physical and digital worlds continue to mesh, and digitalization is becoming more pervasive. In order to continue to make the kind of social and economic progress to which we have become accustomed, we require increasing levels of data to better understand and operate in the world around us. This is an era of progressively bigger data, as the data being generated and stored continues to double about every 2 years. From 1 zettabyte of data in 2010 to a predicted 44 zettabytes around 2020. Finally, the result of these dynamics is that complexity will continue to increase at exponential rates, and innovation cycles will continue to speed up. So now let's consider our context. The hardware paradigm underpinning the information and communications technology industry has experienced 3 major shifts over the past 60 years. The mainframe era, the personal computing era, and the Internet of Things era. During this period, the user-to-device ratio inverted. The mainframe era's many-to-one ratio has become one-to-many. Today, users are outnumbered by the devices that they access, and even more significantly outnumbered by the instrumented nodes on which they rely. This exponential growth in devices and nodes has created a virtuous cycle of pervasive digitalization and automation that is driving an even greater demand for devices and nodes. Now, the $4 trillion ICT industry that is changing how people learn, work, and live is both literally and figuratively built upon the $400 billion semiconductor industry that enables it. Technologies such as artificial intelligence and virtual and augmented reality, as well as companies such as Facebook and Google, rely upon and gain an order of magnitude benefit from our industry. The global economy and indeed society needs us to continue to create and bring new capabilities to market. Now, that being said, the direction and pace of our future advancement is uncertain. As we all know, Dennard scaling ground to a halt a little more than a decade ago, when current leakage grew to such a level that it was no longer possible to further reduce supply voltages in chips. As Moore's law reaches its limits at the deep submicron level due to technical pressures from lithography, power, quantum tunneling, and so on, and economic pressures that have driven the cost of state-of-the-art wafer fabrication facilities such as TSMC's planned 3-nanometer fab to more than $20 billion, it's clear that our industry can no longer rely solely on the classical drivers of advancement in the future. New paths forward have to be charted and different forms of investments made if our industry is going to match or even come close to the progress and pace of the past half-century. Now, beyond these technological issues, business realities are also complicating the path forward. While innovation has always been the lifeblood of the semi sector, in the aggregate, growth is slowing and ROI, return on investment, has become an issue. This environment creates a subtle but steady pressure to de-emphasize innovation as the path to future value generation and shift business models to ones focused more on financial engineering or technical evolution playing a more modest supporting role. Now, while fiscal discipline, of course, is critical, the pressure to de-emphasize innovation has to be resisted vigorously if our industry is to continue to carry its mantle of technological leadership. That continued leadership is critical not just for its own sake, but for the sake of the entire information industry and the even larger aggregation of industries and organizations that increasingly rely on it for their growth and progress also. For example, doctors are increasingly leveraging bits and bytes to make and keep people healthier. Computers are transforming transportation and making it safer, greener, and, of course, more enjoyable. People can communicate, collaborate, and create with virtually anyone, anywhere, thanks today to the spread of digital communications. The reality is that the future will require more, not less, semiconductor ingenuity. So we find ourselves at the center of the proverbial perfect storm. Innovation is being buffeted by technological constraints, business concerns, and insatiable market demand. And yet, our Moore's Law boat is running out of steam. The late physicist and philosopher Thomas Kuhn revolutionized thinking about the advancement of science in the 1960s when he published his book, The Structure of Scientific Revolutions, which overturned the conventional wisdom that science advanced in a linear fashion. One advance built upon another, in a more or less steady but slow march of progress. His contrarian theory was that science's advance was more lumpy, that science lurched from prolonged periods of relative stability, punctuated by dramatic periods of revolution. Now, if Kuhn were alive today, he might describe our current situation as the early stages of a crisis that catalyzes a new paradigm or way forward for the industry. Our industry's existing model will increasingly struggle to respond to market demand within its current parameters. This is the pre-paradigm shift phase, where alternative models begin to compete to become the new model. The reality is that the advent of the Internet of Things and artificial intelligence is decreasing the importance of traditional approaches to and limits of innovation. The Internet of Things and the proliferation of chip-scale sensors and computing elements that intelligently connect the physical and digital worlds are making the Shannon-Hartley limits on information transmission more important than Moore's law. Artificial intelligence, in its push toward neural networks and massively parallel processing, are leaving the sequential processing of Turing and von Neumann behind. In short, the methods by which we measure and pursue advancement are evolving. On the digital side of the industry, teams began managing thermal and clocking constraints in their processing engines and moving to multi-core processing architectures years ago to overcome limitations that couldn't be overcome through scaling alone. Now, on the analog side, issues are being tackled through a strategy referred to as more than Moore. Kuhn would say, these non-Moore's law-based models mark the beginning of a paradigm shift in how semiconductor innovation happens today. The overall industry is increasingly approaching this problem from a perspective that supplements the traditional technology supply-driven approach with an application demand-driven approach. The technology supply-driven perspective focuses on driving improvements along the primary dimensions of performance, size, cost, and power efficiency, for example. Whereas the demand-driven perspective starts with the problem to be solved and works backward from there to more efficiently and effectively align inventions to applications. In this combined technology supply and application demand era, there are three principal areas in which ADI has been investing to drive future innovation, and I'd like to share some of our progress with you here today. The first area is the technology layer. The primary dimensions of innovation in the Moore's law era have been reducing gate lengths and other critical dimensions and increasing wafer sizes to achieve scale and convergence around a limited number of nodes, what the ITRS refers to as Moore. The sure and rapid pace of hardware advancement in this era enabled the entire technology stack to predictably plan for the future of capabilities and needs quite easily, but on the downside, allowed inefficiencies to creep in. For example, in the development of software, programmers didn't really need to worry too much about producing code that made the most efficient use of hardware resources because they knew the hardware would cover those inefficiencies in a very short period of time. That won't work in the future. In contrast to the convergence of Moore, more than Moore is characterized by divergence of technology scope. It is combining and layering technologies with silicon to achieve something completely new. It ranges from new materials and adding more elements from the periodic table to employing process and package technologies to create novel passive and active devices and more complex and complete system-on-chip hardware architectures. Now, for example, the image you see on the screen here is ADI's chip-scale pH sensor technology, which promises to bring lab instrument quality performance to the field in a zero-pin, tiny form factor and at a cost that opens up entirely new applications in industrial, medical, pharmaceuticals, and so on and so forth. This is only possible in a world where we're leveraging clean rooms, semiconductor manufacturing equipment, and other types of equipment and processes as well to develop extremely small, extremely precise, non-silicon-based products like sensors. In fact, there is no semiconductor content at all in this pH sensor element. Instead, we're leveraging known manufacturing techniques such as electroplating and wafer bonding, which with features you would never see on a CMOS wafer or anywhere near a silicon clean room, such as gold, microfluidic channels, and even liquids. Now, this slide gives you a sense of how things are changing. As you can see, the number of elements upon which we are relying has more than doubled over the past decade. That isn't to say we avoid silicon in more than more. On the contrary, we are combining these sensor elements with ASICs. Developing the sensor and electronics together opens a variety of possibilities and advantages. The combined solution is ultimately of higher performance, and we can closely couple the sensor and electronics, tailoring one for the specific advantages and disadvantages of the other. Also, we can use the ASIC to monitor the sensor and enable a smarter solution, one that can compensate for drift in the sensor, for example. Finally, sensors can provide additional indirect and subtle sources of information. What may appear to be noise that we can extract from the sensor via the active circuitry and combine with the primary measurement to make a more precise or valuable measurement. For example, by incorporating additional electrodes on our sensor, we can capture temperature and conductivity measurements, as well as pH, providing additional information on the species or reactions occurring in the sample. We're now well beyond the realm of simply miniaturizing a pH sensor. Aside from materials innovation, advanced packaging technologies are becoming increasingly valuable in product development, as demonstrated by the micromodule technology that our linear technology franchise developed and has refined over the past 10 years. During this time period, the power density of these products increased by more than a factor of 10, primarily due to creativity in 3D packaging techniques and magnetics. Through clever integration of passive components, developing novel thermal management structures, and incorporating advanced interconnect techniques such as copper pillars, the size, efficiency, and thermal performance were all optimized. Today, one small module can deliver the 100 amp load that previously took 12 modules in 2010, and do so without frying the board. This matters not just to our customers, but to our customers' customers as well. For example, in data centers, the largest operational cost is the electricity needed to cool the equipment. If improving the thermal management of power supplies can reduce cooling needs by just 1 degree Celsius, millions of dollars in electricity costs can be saved annually per data center. Today, we're adding power system health monitoring features that constantly measure and analyze the status of the power system, measuring performance, correcting drift, and watching for warning signs of impending faults. By communicating with the processor and reporting that data, the power system performance can be adaptively optimized. In essence, more than Moore is enabling smarter power. Once we begin adding capabilities like cloud-based analytics, however, I would argue that we've entered a new realm that is more than Moore. Once we begin adding big data analytics, algorithms, software, and security, essentially building out the complete integrated technology stack beyond hardware, we're now in beyond Moore territory. And when these three axes of technology innovation are combined, we free ourselves to deliver more comprehensive and a much wider array of solutions to the market. Thinking expansively about technology advancement is key to our industry's future. Secondly, we need to pursue innovation at the physical system layer, shifting our focus from the internal to the external, from ourselves to the world around us. This level draws on insights, inspirations, and advances from the world in which semiconductor technologies are being applied to drive us forward. Now, I realize that taking an application-centric approach isn't new to this industry. After all, ASICs have been around for nearly 40 years. What is new is the level of insight we now have into physical, chemical, and biological phenomena, insight that inspires and shapes our product developments. When we begin to go beyond merely knowing an application's technical problem to a deeper understanding of why the problem truly matters, as well as the business context in which our solution can be applied, a new realm of possibilities opens for us. That's why ADI invests not just in exceptional analog, digital, and software engineers, but also chemists, cryptographers, biomedical systems engineers, and even physicians to ensure we fully understand the applications we are seeking to address with our technologies and capabilities. Now, take, for example, our work in energy, one of the largest industries and markets in the world. Recently, IoT has become a very hot topic, but utility companies' advanced metering infrastructures, or AMI, were IoT before IoT was even cool. AMIs are the vastly distributed but integrated systems of smart meters, communications networks, and data management systems that utilities use to remotely monitor energy generation and consumption. All of those millions of meters must be periodically monitored to ensure they don't drift in accuracy and begin overbilling customers. ADI set out to solve the meter accuracy problem with a complete edge-to-cloud, non-invasive monitoring solution that reports on meter accuracy and sensor health while the meter remains in the field. In essence, we do this by injecting a tiny but very stable background signal into the sensor. We then pull that signal back out from the unknown energy signal, which may be more than 130 dB larger, using advanced signal processing capabilities. This process, combined with system-level understanding and a cloud-based analytics service, allows us to discern the most minute signal changes and diagnose the sensor and meter irregularities they can indicate. But the most interesting aspect of this example is what we discovered when we worked with our customers and began to better understand the industry and its market dynamics. The energy sector loses almost $100 billion of value every year as a result of electricity theft. That's 1/4 of the value of our entire industry every year. We realized that our product could also be deployed to detect and locate tampering and give utilities the information they needed to stop it. In this case, simply understanding the larger context of our customers and their markets opened up an entire new application and revenue stream for our technology. The final side of our triangle of innovation addresses the growing complexity of applications. To adequately address that complexity, suppliers need to start looking beyond their four walls and begin truly innovating as an ecosystem. That's to say, the challenges we're working to solve today are sometimes beyond the capabilities of any one supplier, no matter their scale or their scope. In our world of increasing complexity, collaboration across ecosystems will become increasingly critical if we are to tame it and create an effective match between technology solutions and market needs. When collaborating as an ecosystem, suppliers must be clear about the areas where they are unique and should strive for leadership, but also the areas where they should take a federated approach in which they leverage formal and informal partnerships to advance. As ADI's CTO Peter Rail is fond of saying, you have to know when to lead, when to follow, when to co-invent, and when to partner. Ultimately, this needs to be a win-win relationship for all parties in order for the ecosystem to be successful. When the three sides of this triangle are coordinated, we can generate inspiring innovation and, importantly, create real market impact. For example, this is our general-purpose software-defined radio. ADI first tackled the SDR challenge by introducing a single-chip, low-power MIMO transceiver comprised of 2 transmitters and 2 receivers. This transceiver removed much of the hardware complexity from our customers' radio designs by incorporating that complexity within our chip. And in addition, software-oriented customers could fully leverage the sophistication of the chip in their native software domain. As a result, this product has been deployed in hundreds of applications, ranging from camera drone video streaming and control to cellular base stations. Recognizing the multi-application potential of the transceiver early on, we sought to build an ecosystem of complementary products and services to better support and ease our customers' design and efforts. We built an ecosystem of simulation tools with MathWorks and a variety of third-party hardware and software packages to shrink the development gap between systems architects, RF designers, and systems software developers at the beginning of their software-defined radio design journey. Thus, we're enabling more elegant and efficient designs and a faster time to market. This chart shows the diversity and number of organizations we are working with on the back end to ease our customers' front-end experience. As we worked with our SDR customers over the years, our teams gained a deeper understanding of the environment in which we are operating, particularly the new form factors for cellular base stations and the challenges created by the exponential growth of cellular traffic. This led to the evolution of our relatively simple general-purpose SDR to the much more complex solutions for cellular infrastructure applications that we offer today. Using roughly the same architecture, many of the critical specifications of our product were improved by up to 30 dB through a combination of circuit-level innovation and digitally assisted algorithms. Now, shown on the right of this triangle, the top photo is an RF transceiver for 3 and 4G radios. The product below adds macro 2G support, which increases the dynamic performance by another 20 dB. This product, which will be described in paper 9.3 at this conference, provides the footprint reduction that communications customers crave, reducing a many-chip solution into a single chip and eliminating many impossible to integrate components, such as IF filters. Finally, the photo on the left of the triangle demonstrates how we are leveraging more than Moore, and beyond Moore to create our next generation SDR solution. Returning to our up-the-stack diagram, we've gone from a solution that covers these dimensions to one that covers these dimensions. Moving to 28-nanometer RF CMOS, we are doubling the number of RF channels and adding algorithms such as power amp linearization, receive path linearization, crest factor reduction, and noise cancellation to address the challenges of delivering 5G solutions that improve spectral efficiency by dramatically increasing the number of antennae. This is the power of expanding the aperture of your innovation to include technology, physical system insight, and ecosystems. Now, the fusion and expansion are built into the DNA of innovation. Technologies spread out, combine with other technologies and techniques, and continue growing and sometimes spawn entirely new technologies, businesses, and markets. As we stand at the end of the eras of Dennard scaling and Moore's law, our understanding of how we can continue to grow and evolve in the future has to become much more expansive. I've been in this business for about 35 years now, since the tail end of the first wave and the start of the second wave of the ICT industry. I've lived through the supposed golden age of semiconductors and have seen some amazing advances. But as I stand here now and think back in those past 35 years, I really wish I were starting all over again. I say that because there is such tremendous need for creativity as the physical and digital worlds increasingly intertwine and create new opportunities to solve problems that have bedeviled humanity for decades, for centuries, and even longer in areas of healthcare, environmental degradation, security, and the need for communication and learning that breaks down barriers and opens up possibilities everywhere across the globe. Semiconductors play a critical role in engineering our social world. Secondly, we have at our disposal a trove of technology tools, of capabilities and building blocks, and insights that are ripe to be combined into novel and more powerful combinations. And this goes further than just semiconductors when you consider the combinatorial possibilities with sensing, computing, and communications technologies. All that we need as an industry is imagination and courage. We need to put aside the cynicism and pessimism and reclaim the optimism and enthusiasm with which our industry has been marked since its beginning. Ours is an industry with a rich history and heritage of ambitious, revolutionary characters. The industry needs to reignite its zeal for pushing through what were perceived to be impossible limits and its flirtation with the bizarre. It's time to throw off the shackles of Moore's Law, which in some ways has been the antithesis of creativity. It was a roadmap that we slavishly followed into multi-million-dollar masks and billion-dollar fabs. To be sure, the solutions to the technical problems encountered on that journey were really, truly inspired. And this conference is the annual celebration of that ingenuity. Compared to the open field of possibilities we face now, however, the Moore's Law era was a relatively constrained environment about more bits, higher speed, lower power, and so on and so forth. The direction was clear, and the future was calibrated. Not a lot of thinking required. Now that the Moore's Law train is rolling to a stop, we can finally get off, look around, and really do some interesting things together. Thank you.